Welcome to Ethnic Media Services weekly national news conference. I'm Pilar Marrero, Associate Editor of EMS and today's moderator. Our topic today is exploring outer space, why we do it, and what we learn. The James Webb Telescope recently brought us new images of all stars and constellations, filling our minds with wonder. Looking at one of the most impactful of those photographs, one of our panelists wrote, quote, "The endless riches of the deep field image, jam-packed with stars and galaxy, covering a tiny patch of the sky, tells the history of the universe." End of quote. The images also filled us with questions. Is there other life in the universe? What kind? What do other planets look like? Will we be able to take regular trips to the moon and Mars in the future? All those questions are being explored right now by several countries, including the United States, that have been investing in different projects and technologies that help us look beyond our own planet. And we have a bigger question. Can space exploration in all its facets help humanity discover the answer to essential questions, including finding the keys to our survival on Earth? To explore these issues, this week we have, pun intended, a stellar panel. First, Alexandra de Castro, Science and Technology Communicator with Pascal, and also from the Space Telescope Science Institute, Nicole Arulanantha, Giacconi Postdoctoral Fellow. We welcome Alexandra de Castro. She joins us from Europe today. She lives in the Netherlands, in The Hague. And she's a science and technology communicator. And she's going to have a presentation for all of us. Ale, bienvenida. Welcome.
Okay, so thank you very much, Pilar and Sandy, for the invitation to your media briefing. I'm very glad to be here sharing with you some of the knowledge on astronomy and space I've accumulated through my career as a science communicator. And so, first of all, I would like to introduce, because the other panelists will introduce, I will introduce our next adventure on human space exploration, that is Artemis. And so this here is a artistic impression from ESA, right? And Artemis program, which is a sister of Apollo, is aiming to take humans back to the moon, okay? But this time is not just to prove that we can do it, but to stay. The plan, the long-term plan, is to settle actually there, to build a lunar base. And well, it's a dream. This is a dream, but many people are working hard to make this dream happen, right? So then we will start with Artemis 1, which is the first mission, of course. And this mission is a test mission to make sure that traveling to the moon for humans for many days, 40 days actually, is safe, okay? So because Apollo missions were very short missions, just go there, stay there, walk a little bit and come back. The longest was 12 days. And actually that was very audacious because we didn't know back then the risk of space travel for humans, but now we have a lot of information from the 20 years of experience with the International Space Station, right? So, okay. So this is here, this rocket is the Space Launch System, which is now in the Kennedy Space Center in Florida, ready for launch, and is going to be very soon, now probably September or October, crossing fingers. And on top of the rocket is the Orion capsule. Here the humans will go. But as I said, Artemis 1 is a test flight. It is uncrewed. No real astronauts will go there. Just they will put some human-sized dummies to investigate. They will put some detectors for radiation, so we can know the amount of radiation the astronauts will endure. And then in Artemis 2, which is going to be in about 2 years, they will take 4 astronauts to the moon, and hopefully, according to the plan, they will take the first women astronauts to the moon, because they were missing in the Apollo project, right? So, and this is a short-term plan, and there is a medium-term plan before we go to build the actual base camp, because the base camp is a long-term plan. So this medium-term plan involves the construction of a space station orbiting the moon, instead of like our International Space Station that is orbiting the Earth. This one, which already has a name, is Gateway, will orbit the moon, and the astronauts will go there to live and work in this controlled environment, right? And they will stay there for 6 months, about 3 to 6 months, and they will use the Orion modules back and forth from the Earth, and some vehicles for food and supplies. And of course, they will have the lander, so they can go actually to the moon and work on the moon, and many robots which will help with the heavy work, right? So this is a medium-term plan. And as I said before, in the end, what we want to know, what we want to achieve is to learn a lot about the moon and how we can build a base to stay on the moon, a base on the surface, okay? So why are we doing this? So this is what we are here to discuss. Why are we doing this? What are the benefits for society of human space exploration and astronomy as well? Well, I have this here, this picture I took from Wikipedia. This is the Beagle. I don't know if you remember this, the name of this boat. This is Charles Darwin's boat. He explored the whole planet. I mean, not the whole planet, but he and Humboldt and many others explored many places on the Earth. And they found many new species and clues about life on Earth in such a way that Darwin could propose his evolution theory. And actually, evolution is not just a theory, it's a fact. It's something that is happening right now as we speak. So, and what is this? Is curiosity, is we're hungry for knowledge. We want to know many things. And this is what makes us humans, actually. I would lie if I would say something like we are going to space because we want to do something good for a society. No, we are doing this astronomy and science because we are hungry for knowledge. Okay, and so going to the moon is not different from what Darwin and Humboldt were doing. It's just that our environment got bigger. The outer space is now part of our environment, and we want to just keep going, okay? So let's go to the actual benefits. I'm speaking too fast. No, not too fast. Okay. So what are the benefits, right? Well, there are many benefits, actually, many benefits. And the first of them I want to speak about, this is the one that I like more, is new knowledge, okay? So knowledge is something that you cannot touch or have in your house, but it's something that we can use for our benefit. It's any kind of discovery can be used for the benefit of communities, the nations, and we just need to understand how to empower ourselves through this knowledge, through the new knowledge that we acquire. And for this, I would like to show you two examples, okay, of this wonderful knowledge that we can acquire actually by human exploration. And for that, I share with you this video. This is a video from Apollo 15, and it's a crappy video because it's very old. It was done on the moon and with a not the most sophisticated camera, because you could not bring a heavy, sophisticated instrument to a camera to space. Okay, so this looks like a simple experiment for him, but it was done far from the Earth. It was done on the moon, and I think this was a big moment for humanity. It was a confirmation of how gravity works in other places, not just on Earth, a confirmation of the laws of nature that Galileo, Newton, and others deduced for us. And everything around us, the transportation system, our houses, bridges, buildings, the world as we know it, use these laws of nature. And this is the kind of knowledge that we can get from exploring the space. This kind of video, for me as a physicist, this gives me goosebumps. It's so beautiful. So thank you for your time.
Thank you, Alex. That was beautiful. I loved it.
Thank you.
So let's go to the next speaker because our time is going to be tight today. We'll leave questions for the end. Let me welcome Nicole Mann. She's a Giacconi postdoctoral fellow at the Space Telescope Science Institute, and she studies planets. Welcome, Nicole.
Sorry, Can you hear me now?
Yes.
Okay. Sorry about that. So I'm really excited to tell you all a little bit about what I study here at the Space Telescope Science Institute. So my main area of research is studying the formation of stars and planets in orbit around those stars. So I wanted to show you an artist's impression of what this environment might look like. Now we have really beautiful images of different specific components of these systems, but I hope by the end of the presentation, you'll see why it's hard to look at all of these things at once. So we have this really nice artist's impression that was made by scientists at the European Southern Observatory. And at the center of this image here, we have this ball that represents our very young, bright star. And this big ring, this brown ring of stuff, is what we call a protoplanetary disk. And this protoplanetary disk includes gas and dust and all of the constituents that will eventually be used to form planets. And if you look very closely in this image, you might see a couple of very young planets, very small planets that our artist has drawn in here. Now, when these young stars form, they form from the collapse of very large clouds in space. And something will disrupt those clouds, whether it's a nearby supernova explosion, a really massive star nearby that produces a lot of radiation that can disrupt this cloud. And the cloud will go from a very big kind of stable thing to a shrinking, collapsing ball. And so as the density and the temperature within this ball increase, our core of our star forms. And the remaining material kind of gets funneled into this disk shape. But the star is still pulling material through the disk onto itself in order to grow its mass. And so this creates a very energetic, turbulent, hot environment very close to the star. And this produces a ton of light at ultraviolet wavelengths. And so our eyes aren't really able to see light at ultraviolet wavelengths, but thankfully we have some really wonderful instruments on board the Hubble Space Telescope that are able to collect this light. And so my collaborators and I look at the light from these young stars with the Hubble Space Telescope, and we try to understand a few different processes associated with how stars and planets form. So first, we can use this ultraviolet light to estimate how much mass is being pulled onto the central stars from the disks themselves. And so this tells us how quickly the stars are growing by giving us an estimate of how much stuff is being pulled onto the star every year. We can also use this light from the Hubble Space Telescope that we observe with the Hubble Space Telescope to determine how much this ultraviolet radiation is interacting with the material in the protoplanetary disk. So we can get a sense of how the energy from this light goes into the molecules in the disk. And it actually can heat the molecules up so much that they have enough energy to escape the gravitational influence of the star. And so this is very interesting, right? Because the stars themselves are controlling how long the planet-forming material stays in these protoplanetary disks. The stars themselves are removing the material by either pulling it from the disk onto themselves or by blowing it out of the system in those really nice outflows that we saw in the JWST images. Something that I'm really interested in studying is how this ultraviolet light influences chemistry in this planet-forming material. So the light is, again, very energetic. And this means that it's able to, first of all, pull gas off of dust and ice grains. And so it can essentially turn some of the solid planet-forming material back into the gas phase. It can also strongly influence formation of molecules in the gas that will eventually form planets. So for example, species like methane and ammonia are very sensitive to the amount of ultraviolet light coming from the young stars and reaching the gas. Now, once this gas is actually incorporated into the atmosphere of a young planet, there's a lot more chemistry that happens before we observe it as a fully formed exoplanet. But it's really important to understand the initial conditions that are present in these protoplanetary disks, because that tells us the initial conditions of the planets, and we can trace their evolutionary history from there. So we can learn a lot from the ultraviolet light that is generated by these very young stars, but that really only tells us about what's going on in the very, very hot regions right around this star. And so we can think of the star as something like a bonfire. So if you're out camping ever and you put your hands very close to the fire, they'll feel very, very hot. But as you move away from the fire, you get colder and colder and colder. And if you get too far, your feet start to freeze. And that's exactly what happens with the material in these protoplanetary disks. So if we want to get a sense of the very cold material that is located in the disk very far from the star, we actually need to use detectors that can collect light at sub-millimeter wavelengths. So now this is radiation that's much less energetic than the ultraviolet light we detect with Hubble. And this sub-millimeter light is produced by very, very cold material. And so when we look at these protoplanetary disks at sub-millimeter wavelengths, we can see these rings of gas and dust, and they're really beautiful, beautiful images. Now, it's really hard to actually see the little planets that are forming in here just because there's so much stuff in the disk and the planets are very embedded. But we can see the signatures of the planets. For example, we might see a gap in the dust in the protoplanetary disk that might tell us that a planet is there. We might see very big spiral arms, similar to the things we see in galaxies that are driven by planets that kind of produce a wake as they orbit around the stars. And we can also detect all kinds of different species of molecular gas. And so this tells us about the composition of stuff available for planets that are forming very far from the star. So we have Hubble to tell us about what's going on very close to the star with all the very hot material. We have sub-millimeter detectors to tell us about what's going on very far from the star. But what about this middle region? Now, this is where the James Webb Space Telescope comes in. JWST has infrared detectors on board, and these detectors are able to pick up light from very warm material in these protoplanetary disks. So that's slightly closer to the star than the cold, frozen stuff, but not quite so close that it would be destroyed by the really strong radiation from the central star here. Something that I'm really excited to see with JWST is infrared light from molecular gas in these disks. So we will be able to detect light that's produced by molecules like water, for example, which will be incredibly exciting. And there are some scientists who have really interesting observing programs designed to trace how water gets delivered from the very outer regions of these protoplanetary disks to the very inner regions where Earth-like planets might be in orbit. We'll also be able to see molecules like hydrogen cyanide, which is an important carrier of hydrogen, carbon, and nitrogen, which we know have been essential to forming life on Earth. And we'll also be able to detect a whole bunch of molecules that we never dreamed would be possible with this telescope, just because it has been working so beautifully that we're going to have lots of fun surprises to untangle in the data. Another thing that I'm really excited to see in the JWST data is infrared light from very warm dust close to the stars. And we'll be able to look at dust features in particular that are coming from a type of dust grain called silicates. And this will tell us about the composition of that dust. And we'll be able to also explore the size of these dust grains. And the reason we care about the sizes of these dust grains is that we want those grains to grow bigger so that they can eventually collide with each other and form planetesimals. And this is how we get larger and larger planetary bodies. So we want to see the solids in the disk growing, and we'll be able to explore this with infrared emission from these silicate dust grains. And the last thing I'm really excited to see from protoplanetary disks with JWST is actually absorption from the ices in this very cold region. So something that's really nice is that these ices will actually be backlit by light from the central stars, as well as stars that are unassociated with this planet-forming environment. And the ices will absorb that infrared light, showing us exactly how much ice is there to remove light from the background source. And some of the ice results are actually going to be released to the public in the coming weeks, I think potentially as soon as next week, so stay tuned for that. So we have all of these really nice instruments that can collect ultraviolet, infrared, and submillimeter light, but we still have a lot of unanswered questions in star and planet formation. And so scientists across the country are working on technology for the future generations of space telescopes, which will be able to observe these protoplanetary disks at far infrared wavelengths, which will help measure the masses or the total amount of stuff here available to form planets. And we also hope to have a really, really large combined ultraviolet, optical, and infrared telescope at some point in the coming decades, which will let us simultaneously observe the light from these young stars and the gas in their protoplanetary disks. So I know we're running a little over time, so I will leave it at that, and I'll be very happy to answer your questions.
Wonderful presentation, Nicole, and I love that image. We have some key questions that the journalists have been placing in the chat, and we don't have a lot of time, but I think we all think this question, we all have this question. So these data that you've all pointed to, all of this knowledge that we have gathered, and I'm going to go to each of you for a very short answer. Does any of that cause you to believe that there's intelligence life out there? And what about UFOs?
I don't think so. I'm pretty sure there's life somewhere, bacteria or at least simple kind of life in the universe, because there's billions of galaxies and billions of planets and stars and so on. So I think it's very unlikely that we are the unique planet with life. But when it comes to intelligent life, I think we need this more complicated. I mean, it takes more than what we have now with the telescopes to find out if there is intelligent life. There is this SETI project and the Breakthrough projects. These are projects looking actively for intelligent life in the universe, and they have big antennas for radio, astronomy, but just looking into patterns and things like that you can maybe interpret as some artificial kind of signal. But for the telescopes we are talking about here, and the probes that we send to Mars and so on, we are trying to look into simple forms of life and habitability.
I think, this has been a really great summary. The thing that we can detect in the data from Hubble and Webb, and what we're hoping to be able to characterize with Webb especially, are the abundances of different molecules in the atmospheres of exoplanets. And a goal behind this is to be able to detect anything that seems weird that can maybe be attributed to life. Now, whether that life is intelligent, we don't know, but astrobiologists are currently making predictions for what molecules might be signatures of life having formed on another planet. And the work that exoplanet scientists are going to do with JWST over the next 20 years or so will really nail down what a normal atmosphere looks like, so that we can hopefully detect any deviations from that with instrumentation in the future.
Thank you. Bye.